There are two things I'm going to give you the diploma that makes you a corresponding foreign member of this academy, and this is a great pleasure for us and also a great honor for us. And then I will ask you to sign the book of the Academy for Illustrious Academicians.
Okay.
So I don't know if you like to do that now or perhaps after your talk.
Maybe after the talk, yeah, I'd love to.
Thank you, and I hope that we could eventually take a collaboration between your group and the Academy or whatever.
Okay,
So,
thank you.
Thank you.
Thank you very much. Well, I think we have to switch the screen, don't we? Yeah?
Oh.
Ah, here it comes. Okay. Yeah, thank you very much, Miguel, for the invitation. And I'll try not to go on too long, but I wanted to tell you a little bit about what has happened since 2005. Here we are, okay. Because the story begins a long time ago, actually in 1956. So it's an old reaction going back to the early days of DuPont. A man named Herb Eleutherio, proposed, I won't go into detail because I don't have time, that it was possible for olefins to become split and to redistribute the ends. For example, in this unsymmetric case, to become in equilibrium between the unsymmetric and the two symmetric olefins. Ultimately, that became known as olefin metathesis. It went through other names, but that's the name it's known as now. Yves Chauvin, as was mentioned by Ernesto, was the one who first proposed the mechanism. He proposed that there was a metal-carbon double bond species of some sort, ligands unknown, that would react with an olefin to put the two R groups next to one another. That would give the symmetric olefin and a new carbene or alkylidene. And then that reaction would take place again to yield the other olefin and this old first carbene again. So that was proposed in 1971. So between about 1974, when I made this discovery that Ernesto talked about, tantalum, carbon double bonds, and 1986, when I was at DuPont, between 1975 and 1986, and still am, as you heard, we developed molybdenum and tungsten catalysts because they were the metals that catalyzed this reaction naturally. Bob Grubbs, as you also heard, developed in the early 1990s ruthenium catalysts. So that's where the three of us got to know each other through metathesis. Now, the reaction I just showed is not very interesting. This one is not an interesting reaction because you don't make a specific product. But the other reactions shown here are more interesting. Coupling to give ethylene and this symmetric olefin, a cross coupling to give ethylene again and the unsymmetric olefin specifically. You can make polymers by opening up strained rings. So this is called ROMP, ring opening metathesis polymerization. I may have time to mention a little bit about that. And then Bob Grubbs showed in about 1992 that you could make rings that were not strained in this ring closing reaction, so-called ring closing reaction. And you can run this reaction backward, and there are many other reactions that are possible with the metathesis technology. Now, one thing that remained an unsolved problem at the time of the Nobel Prize was the fact that, of course, olefins can be cis or trans. And you would like to make one of them, not both of them. Very often, the trans is the predominant product, and it's usually about 4 parts of trans to 1 cis for thermodynamic reasons. So this is a thermodynamic equilibrium in many cases between cis and trans. It would be nice, since many of the natural double bonds are cis, to be able to make cis double bonds only. So that was an unsolved problem. We have to have some sort of selectivity for that. Z or cis first, and maybe later E or trans. So for the first 10 years, I guess, since the discovery or development of molybdenum and tungsten catalysts, I call these the first generation catalysts, we were making bis alkoxide, molybdenum or tungsten, alkylidines. This is the initial alkylidine, but we know that it switches, of course, during the reaction. And then this ancillary ligand, supporting ligand called an amido ligand. So many variations could be made of these catalysts. Many variations that depend primarily on what kind of alkoxide is present, very electron withdrawing alkoxide or very electron donating alkoxide. One thing that we found out at that time, and is still a problem that I'm not going to go into much detail at all about, is that there are actually two isomers of these compounds. One has the substituent, whatever it is, in the same plane as carbon, metal, and nitrogen, pointing toward the amido group. We call that the syn isomer. And the one where this is pointing away, kind of a trans or anti-isomer. The rate of interconversion of these in the absence of an olefin can be very, very fast, as fast as 10 or 100 per second, or very slow, 10 to the minus 5 per second. So many orders of magnitude difference in rate of interconversion, and since they are different compounds, they react differently, they behave differently, and so it's a complicated situation, especially if they interconvert, or even if they don't, to deal with. We know that the bond is about, the strength of the bond is roughly, or the barrier to rotation is roughly 20 kcals. So these are rotating readily, and these at the top are not rotating rapidly at all. The second generation catalysts were enantioselective. So you just join the oxygens together with some enantiomerically pure ligand, biphenolate, binaphthalate. You notice the amido group is the most effective one, is now this dichlorophenylimido group. And then you can make enantiomerically pure products with this chiral enantiomerically pure catalyst. So this is a very high yield, which is one of the great attractions to metathesis, very high yield, and 97% EE at that carbon, so very high enantioselectivity. So I've written more than 40 papers in collaboration with Amir Hoveda, who's an organic chemist, on this enantioselective version of olefin metathesis. You can also make polymers with these species, and they have specific structures, and maybe I'll have time to mention them as I go along. But the problem, the bad news and good news, is that you have many possible catalysts. You can make many possible catalysts. These are just a few of now the bidentate type ligands attached to the metal, a few of the amido groups, and you really want to have some way to make catalysts in situ, just to add ligands and make and test the catalysts one by one. And we decided it was not obvious, but it turned out to be that the precursor that would react with an alcohol, we thought, would be what is shown here. This is a BISTpyrrolide. This is a 1- ligand. It can be protonated by alcohols, and you can make a bis alkoxide from it, and also then in the process, as we'll see, the the Pyrrole, which is not a reactive species. It does not bind to the metal. So this is likely to be a good precursor to bis alkoxide catalysts. We have many crystal structures of these species and know a lot about them as precursors, but we're not interested in them per se. We're interested in converting them to bis alkoxides, or were in the beginning. So this is the reaction we wanted to do. Add alcohol twice to generate two equivalents of Pyrrole, here dimethylpyrrole, and the desired bis alkoxide. And we did that. We showed that the pyrrole that is generated is not binding to the metal, not interfering with the catalytic reaction. So you can make many catalysts from these precursors, putting on different alkoxides and testing them. An intermediate in that reaction is the subject that I want to talk about tonight, the so-called monoalkoxide pyrrolide species shown here. So that's formed sometimes selectively, and you can crystallize it out. And we expected it not to be very reactive, somewhere between this species, which is not very reactive, and this one, which we know is highly successful for the metathesis reaction. But it turns out that these, for reasons that are not clear, are in general probably 100 times more reactive than these. So we don't know why. One possibility among many is that the metal itself is unsymmetric. It's the chiral center. That's not new in organometallic chemistry and inorganic chemistry, but it is unusual for a catalyst itself to have an unsymmetric center, and it, as you'll see, is really a very important feature of the catalytic reaction. And the fact that all the intermediates are not symmetric in some way, but distorted, is perhaps why they turn over, the catalyst turns over rapidly. So these are very highly reactive, these MAP species. The structures are not unusual. The pyrrolide is bound only through the nitrogen. So these are 14 electron species as we count them. They can react with olefins. There's plenty of 2 orbitals to use to bind an olefin and form the Metallo cyclointermediate and so on. Now, the stereogenicity of the metal center is really something that we didn't appreciate in the beginning, but thought that it should be possible to use that chirality for asymmetric reactions. Now, a man named Henry Brunner had the idea that chirality at the metal, if you could use it for a catalytic reaction, was the most powerful chirality, most powerful determinant in an enantioselective reaction, which usually, after all this time, decades, really depends on steric factors, some sort of chiral ligand that sterically prevents a substrate from attacking the metal one way versus another. Here you have 4 different groups. The substrate will attack the metal on one of the 4 faces of the tetrahedron and form a 5-coordinate intermediate. In order to control that chirality, we have to make diastereomers. So we attach an alcohol that itself is enantiomerically pure, and then you can have chiral compounds that have one chirality at the metal center and a fixed chirality. This one happens to be R in the ligand, or the other configuration at the metal and R in the ligand. So this is S at the metal, R in the ligand, R at the metal, R in the ligand. These are configurationally stable. They can be isolated and characterized. These are crystal structures, and then used in various reactions. And this is one of those reactions that was being explored at Boston College by Elizabeth Sately, who was a graduate student of Amir Hoveda. She devised this synthesis of this tetracyclic alkaloid called quebracholine. So there's the chiral center, and it involved a metathesis reaction at this point where the metal attacks here first and then closes to form this ring. That's a ring closing reaction, and then hydrogenation yields the product. The problem is that this conversion from here to here was never possible with any molybdenum or tungsten catalyst that we know, and no ruthenium catalyst, and there are very few of those. There was simply no conversion. But the only catalyst that worked, in fact, poorly, was this symmetric catalyst. It's not an asymmetric catalyst, not an unsymmetric catalyst. It's a bis-hexafluorotebutoxide, so-called Schrock catalyst. But there are many. This is just one, and of course it's not enantioselective. But these MAP catalysts, like the one I just showed you with the dibromide ligand, as a diastereomer, actually as a mixture of diastereomers, works very well. 2 mol% or 1 mol% in the case of the dichloro ligand. 1 hour, 98% conversion, good yields, and very high EE. So this is surprising. We reported this back in 2008. Because if you have 2 diastereomers, if you have chirality, 2 different chiralities at the metal center, as some mixture, let's say 2 to 1, the mixture that I showed you, 7 to 1, is actually the kinetic mixture, not the thermodynamic mixture. Thermodynamic mixture is about 2 to 1. Then you should get these 2 counteracting one another and not giving such a high EE. So how does such a high EE arise? Well, it's a very now pretty well understood general phenomenon where you have 2 species in equilibrium, the 2 diastereomers that are possible. I show them as methylene species here for simplicity, the one that is S at the metal, and then the chirality in the ligand, or R at the metal. But this one basically is a relatively slow catalyst, relatively slow. We don't know whether it's absolutely slow, but it's relatively slow. It's converted readily into the fast one, and the fast one gives product in high EE. So the answer is that only one of the 2 diastereomers is reactive enough to make product, and it makes it very well, very high EE. The 2-step process in this case actually preserves the chirality at the metal center. S goes to R in the intermediate and back to S, so you can continue to make product. If you make any of this one, then it rapidly gets converted into this one in the process of reacting with any olefin, especially ethylene, which is a product of the reaction. This was reported in 2009. We had a very good year in 2009. I think we published 10 papers on these new catalysts that were appearing every day, practically. We became interested in what the intermediate is in the reaction, and it has to be a metallocyclobutane. So if you take one of these MAP catalysts, this happens to be one of the diastereomeric versions, and add ethylene, you do make a metallocyclobutane, unsubstituted metallocyclobutane, which is the most stable of the metallocycles towards loss of olefin. And it has this shape, a trigonal bipyramid, big. This is this big chiral ligand that I mentioned at the bottom, and the diisopropylphenylamidal group at the top. There's the metallocycle and the dimethylpyrrolide in the equatorial plane of this trigonal bipyramid. Very nice, highly crystalline compounds that precipitate out. This is a crystal structure of that compound. And we propose that all intermediates, although we haven't seen any substituted ones yet, have that structure. That'll become important in a minute. So the key proposals are that these are the metallocyclobutane intermediates in the reaction. An olefin arrives trans to this pyrrolide on the imido-alkylidine oxygen face, and it makes a metallocycle, which then forms product, and the alkylidine migrates around to the back to form the new alkylidine. In the process, you invert the configuration at the metal from R, which is what is shown here, to S. That's a requirement for all reactions involving the metathesis reaction itself. And all of this is supported by DFT calculations by Odile Eisenstein in collaboration with Christophe Copperet, now at the ETH. We had a surprise then. So Amir Hoveda was involved in cross-metathesis reactions. These are called ring-opening cross-metatheses. So this is the product that you should get. And of course, this is should be an enantioselective reaction, we hope. But this particular reaction for this particular catalyst simply did not work, no conversion. It's very characteristic of these new catalysts because they are very, very sensitive in many ways to everything around the metal. And so to find that some reaction doesn't work is not surprising. If you change the amido group to adamantyl amido, then the reaction does work very well, greater than 98% conversion, 85% yield, 97% EE, and this double bond is cis. That was a surprise because normally trans is the double bond that is formed. So we began to wonder why this is true. I mean, this is one of the great goals in metathesis, to make olefin products, not that are mixtures of cis and trans, but that are only cis, which is a much more valuable isomer. So we thought that maybe it's the fact that this is a small imido group and this is a large aryl oxide that is responsible for Z selectivity. That is, maybe what is happening here is you do form the same sort of intermediates in a substituted metallocycle, but they all have to point in one direction because this substituent is so large. There's no room to put any of these R groups down. And so the substrate comes in, you make this metallocycle, you make this product, which is Z. It has to be. You make this alkylidene, it reacts again to make this same Z product and go back here, and that's, in fact, the catalytic reaction, a Z selective reaction. So we thought maybe it's a large, small combination that's very important to give Z selectivity in these reactions. Phil Power is at UC Davis in the United States, and he makes very crowded ligands of all sorts. And he made this extremely bulky phenol. This is what I call a hexaisopropyl phenol, terphenol. So it's substituted in the 2 and 6 positions with 2,4,6 triisopropyl phenyl. This ring is turned perpendicular to that ring and does not rotate readily. So this is a very bulky group, as I'll show you. So it's easy to react this phenol with a BISTpyrrolide and obtain a new non-chiral now, large, small combination of phenoxide and imido group. This is the crystal structure of the neopentylidene version of that, a large, small combination, and you can see just how large this is. We managed to make a tungsten compound of the same type, not with an adamantyl imido, unfortunately, but with a diisopropyl phenyl imido, but it illustrated a principle that we think is very important. This is the metallocyclobutane unsubstituted. This is a stick diagram, these are hydrogens, of course, of this monopyrrolide OHIPed hexaisopropyl terphenoxide, which you see here. Now what I'm going to do is turn this into a space-filling model. And when you turn it into a space-filling model, you can see why no substituents can point down. I've colored the 3 hydrogens that are pointing down towards this very large hexaisopropyl terphenoxide. And they are themselves, the protons, touching the protons in the isopropyl groups in the ortho positions of that ligand, here and in back also. So there's no room really to put any other group pointing down. So presumably, if you were to make a metallocycle that had substituents on it, methyl substituents or bigger, and this were a smaller group, those substituents would point up and you would get Z-selective olefin metathesis reactions. One of the reasons why these compounds, these catalysts, are so efficient, besides the theoretical calculations that I told you about, is because the big ligand, like this hypto ligand, makes even methylenes, which are the most unstable alkylidene intermediates. They decompose bimolecularly very readily, stable enough to isolate, and therefore they are probably stable enough to last for a very long time in the reaction, and so you get many turnovers instead of rapid decomposition. So these large ligands are helping us to prolong the life of a catalyst in these metathesis reactions. So is it possible to do Z-selective couplings? So this is the grand prize of metathesis, and the answer is yes, it is. Using these types of compounds I just mentioned, for the reasons that I just mentioned. A substituted alkylidene will react with a terminal olefin to give one of two intermediate metallocycles. This is the one that will give rise to product, and that product has to be Z, and the methylene species will react with this olefin to give ethylene and go back to this species. So this is possible just by restricting, as I said, these R groups to point up. There are ways to make trans products. There are several ways. One is simply to not get this intermediate, but the trans one, and then you get the trans product. But we don't think any of these other possible ways of making an olefin, which is trans, are possible, take place rapidly. And it turns out that the catalysts that work are tungsten catalysts. And the reason happens to be because it's tungsten, we found out, is much less reactive than molybdenum. Molybdenum is about 5,000 times more reactive than tungsten, and therefore isomerizes the product, the Z product, to the thermodynamically more favorable E product. So you get a mixture of about 80% E to 20% Z. But tungsten does not, because it's not active enough. It's actually active enough to do the coupling, but not active enough to isomerize the product. So this too was reported in 2009. Here's a large table. I'll just point out a couple of things. One, the OHIP ligand, with one exception, is the only one that is successful. Two, tungsten is the only metal that is successful. And three, it doesn't appear that you need a small imido group. Any substituted imido group, diisopropyl, dichloro, or dimethyl, is successful for tungsten. It takes time. The temperature doesn't go at room temperature, so you have to heat up between 80 to 120 degrees, I think, in one case. The loading is anywhere from a typical 1 or 2% down to as low as 0.1%, I believe now. But the yields can be high, and the percent Z of those yields quite high, greater than 98 in this case of this allylbenzyl ether. Only a 46% conversion, but a 98% Z product, virtually only Z. The yield is not such a big problem because you're making a product that weighs almost twice as much as what you start with, so it's easy to separate the product from the starting material. The tetraphenyl phenoxide, 2, 3, 5, 6 tetraphenyl phenoxide doesn't work at all. We have crystal structures of both these metallocycles. This one I've shown you with the big HIP ligand and the 3 protons pointing down, touching the isopropyl protons, which aren't shown in this case. In the case of the tetraphenyl phenoxide, you would think that's a big ligand, big enough, but it's not big enough in the right way. There's a big hole right here in the middle of this metallocycle so that an R group can point down, and this does not work at all for selective couplings of terminal olefins. So we wanted very recently, and this paper appeared, what's the date? The 16th. This paper appeared yesterday in Organometallics, so this is very recent work. We wanted to make a rapid tungsten catalyst. How do you do that? Well, it has to be a hiptoligand. So here's a hiptoligand. And then instead of a 2,6 disubstituted phenylimido, we move the substituents back to 3 and 5. So this is a smaller version of this substituted aryl imido ligand. This also is a crystal structure of a metallocycle. It's a crystal structure of the tetraphenyl phenoxide, and there's a mesatyl pyrrolide. There are many variations of this 3,5 disubstituted phenylimido group. This one is successful. This one is completely unsuccessful for Z-selective coupling. And this coupling takes place at room temperature. So these are very simple olefins. This is octene, where that is 5. That's a methyl group, so that's 5, 6, 7, 8, 1 octene. It is slow, 4 days, 89% conversion, greater than 99% Z. No E, no trans whatsoever. So this appeared, as I said, in Organometallics yesterday. You can look it up for yourself. 2 mole% now, we think we can get the loading down to much lower than that. So you can actually now make olefins through homocoupling selectively Z. Now some of these don't work as well as others, and that means that you have to change the catalyst a little bit, and that will involve, of course, more research, and we hope that we can make this a general sort of reaction. One reaction that is quite important in terms of using renewable resources like seed oils, corn oil, safflower oil, olive oil, which all have double bonds in them, is to chop up those seed oils with ethylene. That is, run a coupling reaction backwards. So you want to take an unsymmetric, in this case I'm talking about methyl oleate, so this is the largest component of many seed oils. It's available in millions of tons every year. It happens to be a Z olefin selectively, like many other natural products. So it's a C18 with the double bond approximately in the middle. Well, it is in the middle, and this happens to be a methyl ester in this case. So you can run the reaction backward. You can put in 5,000 equivalents of methyl oleate in with the type of catalyst that I've been talking about, the molybdenum bitet catalyst, the chiral one. And you can, at 10 atmospheres at room temperature, I don't think it needs 15 hours, get a greater than 99% selectivity to 1 decene and methyl 9-decenoate in a yield of 95%. So now you can take methyl 9-decenoate and 1 decene and do whatever you want with them. And the whole idea is to use natural, renewable resources as the source of chemicals in whatever you want to do in the chemical industry. Tungsten catalysts don't work because they're simply too slow. Because the metallocyclobutane under an atmosphere of ethylene, or 10 atmospheres in this case, you've got to get the ethylene into the reaction as fast as possible, is simply too stable. It doesn't lose the olefin to form the methylene species, which is the reactive intermediate in this reaction. I want to mention a couple of things. I won't go into great detail, but I want to make you aware that this Z-selectivity is going to have major implications in polymer chemistry, ROMP chemistry. All of ROMP chemistry is not selective, unselective, in the sense that you get a mixture of cis and trans, and you get a mixture of tacticities. For example, this monomer, this norbornadiene, when it makes a polymer, can have cis or trans double bonds, and these rings can all point in the same direction, or one direction or the other. Of course, it's a mixture of all of those. So that gives you a polymer that isn't a single species. Based on what is necessary in a reaction with these MAP species, we can predict that a monomer such as this, these are dicarbomethoxy norbornadienes, 2,3-disubstituted, must react, and again, I don't have time to go through the organometallic details because you probably aren't interested in those details anyway, must react in a way that gives rise to inversion of the metal with each insertion. And therefore, this monomer comes in trans to the pyrrolide from the back. And after one insertion, the next monomer comes in trans to the pyrrolide from the front. And you automatically get all cis or Z syndiotactic relationship between those two groups. And then the next one comes in like this one, pointing forward, back, forward, back. an entirely new structure for a polymer. And it's a single structure. Unlike normal ROMP polymers, this is a single structure. It looks like a small molecule. Greater than 99% has this structure to high molecular weight. Or we predicted that, and it turns out to be true. So greater than, with this large, small combination again, you can make polymers that are all cis and that are syndiotactic with these rings pointing backwards, forwards, backwards, and forwards. Now we can make the cis isotactic with all these rings pointing the same way using a biphenolate or binaphthalate catalyst and show that they are different polymers, entirely different polymers. They have different properties. The glass transition temperature for this one is 115 degrees. We can't observe a glass transition temperature for this one up to 250 degrees. So very different polymers based only upon which direction these rings point. So we reported this back in 2009 also. We call this a stereogenic metal control. It's a new way to control the structure of ROMP polymers and for polymers in general. I could not find another example, or have not been able to find another example of controlling a polymer structure by virtue of the chirality at the metal, one which switches from one chirality to another, back and forth, and back and forth. Stereogenic metal control. Well, we can use then these MAP catalysts to make the syndiotactic polymers. We can make the isotactic polymers, and we can, through a chain end control method that I don't have time to go into, make a trans syndiotactic version. The only remaining one is trans isotactic, and we now think that we can make those also. So you can make different polymers, entirely different polymers from the same monomer, just by making different structures. At one point, it was about 3 months ago, I had this eureka moment when I thought, well, if the chirality at the metal switches in a polymerization reaction, and you have a racemic metal catalyst, and you have a racemic monomer, then there should be one diastereomeric combination that is favored. So the metal will react with one enantiomer, let's say this is the minus enantiomer in this case, and give the first insertion product or an insertion product. The configuration at the metal will invert, and then that configuration will pick the other enantiomer. And so you will get an alternating enantiomer polymer. And that's exactly what happens. So this monomer, for example, this is very easily made in a Diels-Alder reaction. These are dicarbonmethoxy substituted versions. This catalyst is number one, which is not a hipped catalyst. It's a hexamethyl version. The hexaisopropyl one does not work well. So it's too crowded for this monomer, but this one works well. And you generate then this polymer that has alternating enantiomers in the chain, and you can readily show that by NMR studies that that's the case. These are, in fact, the two olefinic protons in that all-cis polymer. They're different, and they're on the same double bond, so they couple with one another. This is a little bit of trans product, so it's not 100% pure. It's greater than 95% one structure. You can do that for the cyano version, same sort of story. And you can do it also for other kinds of monomers, such as this one, this methyl substituted oxen or ornodiene. You get an alternating enantiomer polymer. These are the three signals for these three protons, two olefinic ones and one up here, as shown here. Not for the adamantyl amido, but for the dimethylphenylamido. Everything's very, very sensitive to which amido group you choose and what the groups are on the ligands and what the pyrrolide is and what the metal is and so on. So it's monomer dependent, not surprising. Chemistry is that way. I just want to mention a couple of things about organic chemistry. I know there's probably a couple of organic chemists in the audience, and that is the applications involving these MAP catalysts. One of the most powerful reactions in general, according to Amir Hoveyda, and I've come to believe that, is some sort of cross metathesis, not making homo products like I'm talking about, symmetric products, but crossing olefin A and olefin B to give a product having those two groups in them selectively. I showed you a version of the ring opening cross metathesis with this oxa derivative, and we focused on next vinyl ethers. Now, vinyl ethers are very powerful, and these are enol ethers in the product, very powerful intermediates. There's no way to make double bonds of this sort using any sort of Wittig chemistry or anything you can think of. They're unmakeable. Ruthenium chemistry doesn't work either. Vinyl ethers destroy ruthenium catalysts. But vinyl ethers are perfectly stable with these catalysts, and we can do a ring opening cross metathesis to get a product of the type I mentioned before, where this was a phenyl group, now a vinyl ether group. So enantioselective and cis only, greater than 98%. This is a very fast reaction. You can use less than 0.1 mole% of the catalyst, and the reaction's over in 30 seconds. So it's a turnover frequency of about 60 per second. So we think that we are wasting most of we have, and maybe still are, wasting most of the power of these catalysts because we haven't learned how to use that power. But we're beginning to understand that now. So we are hoping that we're going to have very high turnovers. These are going to become commercially viable reactions, and that's the direction we're heading. This was published again back in 2009. So this is a ring opening cross. It's enantioselective, but what is really important is just the cross reactions, not enantioselective, just the cross reactions, selectively Z. So that would be, let's say, this alleobenzene plus the vinyl ether to give this Z enol ether product. And we can do that with variations of the catalysts I've talked about, 98% Z, greater than 98% Z, greater than 98% Z, very E-selective, and pretty good yields, 82% conversion, 76% yield of the cross product selectively, none of the homo products, or at least no more than 25%. So that's one of the most difficult reactions you can imagine. We started to put this to use. We've begun to make products that are, not me, Amir has begun to make products that are viable, that are found in biological systems or natural products, such as this one called a plasmalogen phospholipid. And this is the enol ether, that little bit right at the end of this phospholipid in this long naturally occurring chain. I think that's a arachidonic acid chain. And it's made in one of these cross couplings shown here. 95% Z, elaborated eventually to this product, this plasmalogen analog. There's only a methyl group here instead of this big ester. And that's now going to appear in Nature as an article on March 24th, about a week from now, I guess. So that is very exciting. That's only one of the natural products in this particular publication. And we're going to write another publication very soon that I think will be able to get into Nature on ring closings, selectively Z, big rings, things that are also found in Nature and or are very useful in terms of their anti-cancer activities. So that's what it's all about. And there are really thousands of catalysts out there now. I mean, that's one of the problems. How do you find the one you need? Well, you can quickly zero in on one that works pretty well, and then you play around a little bit with substituents in order to make it work really well, as I've shown you. This is only the tip of the iceberg, as we say. This is just the beginning. So metathesis didn't end in 2005. I think it's begun in about 2009 in many ways, in terms of applications to organic chemistry and in terms of Z selectivity and ultimately E selectivity, I hope. So here is a Bob Grubbs type catalyst, none of what I've talked about can be carried out with ruthenium. There's no evidence that you can make any olefin C selectively. Enol ethers destroy ruthenium catalysts. So there really are significant differences between ruthenium and molybdenum and tungsten. And I won't go into the details as to why that is true, because I don't have time, but there are some calculations that support that view. So we have a lot of goals. More efficient catalysts, obviously, Z selective catalysts. Kinetically E selective catalyst would be very nice. We have a lot of things to understand. We have a lot of polymers to make. And we are showing that, in fact, you can run ethenolysis reactions that are also Z selective, which is a very good way to take a mixture containing 25% Z and 75% E and eliminating the Z component through an ethenolysis reaction. Well, these are some of the people who have paid the bills, and these are some of the former members in my group who have worked in this area, and these are some of the people who've worked in the area now that I talked about. So I think it's time for me to stop. So thank you very much again for the invitation. I hope you enjoyed the new vision of metathesis chemistry, because I think it's going to be exciting. Thank you.